one of the most common questions that we're always trying to answer is simply, does a series converge? This is an extremely important question. Now, let's start off with the definition and then work on a few examples here. If the limit as n goes to infinity of s of n, this partial sums, equals s, where s here is some real number, then the infinite series n equals 1 to infinity of an exists and is equal to s. In other words, the thing converges to this value s. Now, if the limit as n goes to infinity of the partial sums s of n does not exist, in other words, it diverges, then we say that the infinite series diverges. So let's go back to this example I talked about earlier, this 1, -1, 1, -1. I can represent this as an infinite series. So if I start messing around with this a little bit and start looking at actual values, look at the partial sums, what I'll see is S1, the first partial sum, that's when n equals 1, this exponent is even, so -1 to an even exponent will be a positive 1. S1 equals 1. S2, the second partial sum, will be the first partial sum, 1, plus the next term, well, this is even, or I'm sorry, this is now going to be odd, so I have a -1, so that's going to be 0. S3, the third partial sum, will be the second partial sum plus the next value. Well, this becomes even, so it's going to be plus 1. So this equals 1. And I think you can see S4 is then going to end up being 1 minus 1, which is 0. And this pattern continues on and on and on and on. Therefore, the sequence of partial sums is going to have this pattern of 1, 0, 1, 0, 1, 0, and so forth. Therefore, the limit as n, oops, that's supposed to be an n, sorry, that doesn't look much like an n. As n, there we go, goes to infinity of Sn does not exist. Therefore, this sum n equals 1 to infinity of -1 to the n plus 1 is in fact divergent. This answers that question of what is 1 minus 1 plus 1 minus 1? What does it add up to be? Well, it doesn't. It's divergent. It does not converge anywhere. Now, unfortunately, we can't always find the actual sum of an infinite series. You know, our knowledge in this area is actually really pretty limited. So often what we must be satisfied with is simply determining whether or not an infinite series will converge or not. We may be able to determine that it will in fact converge, but we may not know what it actually converges to. There are some circumstances when we can determine what it actually converges to, but not always. So let's take a look at a couple of examples here. Let's consider this infinite series, n equals 1 to infinity of 1 over 2 to the n. Now I'm going to start writing out some terms here. This is going to be 1/2 plus 1/4 plus 1/8 plus 1/16 plus so forth, etc. Now quickly, one of the first things you probably take a look at is if you take the limit of an as n goes to infinity, this goes to 0. 1 over 2 to the n will go to 0. So that means that this infinite series might converge. It does not mean that it will. It just means that it might. If I looked at this limit of an, as n goes to infinity, 1 over 2 to the n, if this blew up on me, went to infinity, or went to some real number other than 0, I'd say, okay, forget it. We know this thing is not going to converge, and I'd be done. So these terms are in fact getting smaller and smaller and smaller, and it will go to 0. So I'm trying to figure out what will the actual sum of all these go to. Well, to figure that one out, I need to work on this a little bit. So what I'm going to do is I'm going to start writing out the partial sums. These are individual terms, but they're not the partial sums. So S1, the first partial term, will simply be 1/2. S2, the next partial term, will be 1/2 plus 1/4. That's these two added up together, which is obviously going to be 3/4. The next partial sum will be 3/4 plus the next term, which is 1/8, and that will add up to be 7/8. Let's see, the next one is going to be 7/8 plus 1/16, which is going to end up being 15/16. Okay, I'm starting to see a pattern here. The denominator is 2 to the n, and the numerator is always 1 less than the denominator. So this looks like Sn will be 2 to the n less 1 divided by 2 to the n. And if I start putting in values of n, it matches up. So I'm pretty sure that this is correct. So what good that do me? Well, if I know what the partial sum is going to look like in the form of s of n, then I can take a look at the limit as n goes to infinity of the nth partial sum, which in this case is the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n, which equals the limit as n goes to infinity of 2 to the n over 2 to the n minus 1 over 2 to the n. Well, this first term is just 1. So this will be 1 minus the limit as n goes to infinity of 1 over 2 to the n. Now this goes to 0. Therefore, what I have, whoops, it's not 0. What I have is 1. Therefore, the sum n equals 1 to infinity of 1 over 2 to the n is actually equal to 1. So this is a case where I was able to identify Sn, take a look at the limit, and actually determine what this infinite series sums to. So let's take a look at another example. Here, this is just crying out at me to just take a look at partial fractions. This is just screaming out I'm a partial fraction situation. So I'm going to forget the sum right now. I'm going to take a look at this and say, okay, what I have is 1 over n times n plus 1, two distinct linear terms, is going to be equal to a over n plus b over n plus 1, which gives me 1 is equal to a times n plus 1 plus b times n. Now, see, if n equals 0, that means a equals 1. And if n equals negative 1, that means b would equal a negative 1. So what I have is this sum. Oops, that was kind of ugly. Let me see, this sum, that's not much better, but oh well. N equals 1 to infinity of 1 over n. That's just killing me. I'm sorry. I've got to do something about that. Let me see here. There's a little bit better. Okay, we have 1 over n minus 1 over n plus 1. Okay, did that do me any good? Yeah, I don't know. Let's start putting in values of n and see what this is. So this is going to be equal to, see, the first one is going to be 1 minus 1/2 when n equals 1. Plus, when n equals 2, I'll have a half minus a third. Plus, when n equals 3, I'll have a third minus a fourth. Plus, when n equals, where am I, 4, I'll have a fourth minus a fifth. Plus, and this keeps on going, and then ultimately out here I'm going to have plus 1 over n minus 1 over n plus 1. So right away you can see what's going on with this thing. This cancels out. This cancels out. See, the first term of this term right here cancels the last term of the previous. So the 1 over here that I didn't write was going to cancel over here. This 1 over n would cancel with the one previous to that. So what I end up with is this is going to be equal to 1, that's all that's left, minus 1 over n plus 1. Well, this is Sn. So now if I take a look at the limit as n goes to infinity of Sn, which equals the limit as n goes to infinity of 1 minus 1 over n plus 1, this goes to 0, so the sum equals a 1. Therefore, the sum, n equals 1 to infinity of 1 over n times n plus 1, actually just simply adds up to be 1. Now, this is what's known as a telescoping series. And the reason it's called a telescoping series is because everything in the middle here, all this collapses on itself. So you know how a telescope, you pull it out and it gets long, and then you push it back together and it's short again. So I guess that's where the name came from. So let's take a look at another one here. This, again, looks like it's partial fractions. So I'm thinking, you know what? I wonder if this is going to end up being yet another telescoping series. So what I have is 1 over n times m plus 3 is equal to a over n plus b over m plus 3. Because I have these two distinct linear terms. That would then give us that 1 is equal to a times n plus 3 plus b times n. When n equals 0, that means that a must be equal to 1/3. When n equals negative 1/3, so this term goes away, that means that b actually ends up being, I'm sorry, I said when n equals negative 3, not negative 1/3, b ends up being negative 1/3. So what I end up with is this sum, n equals 1 to infinity, of 1 over n times n plus 3 can be written as the sum, n equals 1 to infinity, of, I'm going to factor out the 1/3. 1/3 times 1 over n minus 1 over n plus 3. So now let's start putting in some terms. When n is 1, I get 1/3 times 1 minus 1/4. When n is 2, I'll get 1/2 minus 1/5. This kind of looks like a telescoping series, but not really. I'm not canceling out yet. Let's keep going a little bit here. N equals 3, I get 1/3 minus 1/6. The next one's going to do it for me. So the next term is going to be 1/4 minus 1/7. Cool. So now I can see my 1/4 went away. Yeah, I missed that's a 5th. Yeah, my writing wasn't very good here. This is a 5. For a second, I almost thought it was a 3. Gosh, I don't have anything to cancel this 3 out with, or the 2, or the 5, or the 6. So I need to keep doing something here. Let's go out a little bit more. The next one would be 1/5. Okay, good. I needed that. Minus an 1/8. So now my 1/5 will cancel out. Okay. Plus, next one's going to be a 6. Oops, I should have been in black ink. Sorry about that. Plus 1/6 minus a 9th. Okay, great. My 6 goes away now. But this third, I'm beyond this third. There's no way this third is going to go away. And I can see now that my next term is going to be a 7th. We'll cancel that one. Minus a 10th. Then my next term is going to be an 8th, which is going to cancel here, minus an 11th. So all these terms, as I keep going out, is going to go bam, bam, bam. They're going to start going away. So if I try to consolidate this, it looks like once I get out here that Sn is going to be equal to 1/3 times what's left. I have 1 plus 1/2 plus 1/3. And I'm going to stop there because clearly the 9th is going to cancel out in the next term. And if I look at this for a second, what I've got is this last term is going to be a negative 1 over n plus 3. This term is 1 less, so that's going to be minus 1 over n minus 1 plus 3, which is n plus 2. And then this last one is minus 1 over n minus 2, right? Minus 2, which is this n plus 1. So pick an n, once I get out here beyond 6, 7, 8, 9, pick an n way out here because all these terms are going to go away, and these are the terms that's always going to be left. So if I look at the limit, as n goes to infinity of Sn, what I'm going to end up with is in the limit, this will go to 0, this will go to 0, this will go to 0, and I'm going to end up with 1/3 times 1 plus 1/2 plus 1/3. Which, if I add this up, this is going to be 1/3 times, it looks like 6 is going to be my least common denominator. So I have 6 plus 3 plus 2 over 6, which is going to be 11 over 18. So clearly this is convergent. So the sum n equals 1 to infinity of 1 over n times n plus 3 is actually equal to 11/18. Now these examples, this is, by the way, another example of a telescoping series. I had to telescope out farther to see what the collapse was going to look like. These last several examples I did allowed us to actually find what the infinite series sum to. But as I alluded to earlier, that's not always possible. And we're going to look at here in the future, not too far off, techniques to determine if a infinite series will converge or not. But we may never, ever actually be able to figure out what it truly converges to. We may be able to get a pretty good estimate, but we may never actually be able to find the Sn as such.